Welcome everybody, welcome to JSConf US. Is everyone excited for the great lineup of talks next couple of days? My name is Adam Giese. I am Adam Giese Dev on Twitter, and before I was a software engineer, I attended school for music, specifically music composition, and I was always drawn to the analytical thinking aspect of music theory. And years later, when I started to learn functional programming, I found that kind of the same itch was scratched. So when I started a musical project with web development, I decided to use functional programming. So here's my introduction to functional programming from a musical perspective. So first, we have to ask the question, what is functional programming? Well, it's programming with functions. Just like object-oriented is based around objects, functions are the building blocks. So that leads to the next question. What is a function? Well, a non-functional definition might be something like a sequence of commands abstracted into a reusable unit. But a functional definition is more something like a relationship between a set of inputs and outputs. This is the mathematical definition of a function and is sometimes referred to in programming as a pure function. So, what makes a function pure? First, it means given the same arguments in, it will return the same value. This means that it shouldn't rely on anything from the outside, such as a random number generator, the current time, or a read from the database. It also means no side effects. This means it shouldn't affect anything outside of itself. It shouldn't manipulate the DOM or write to the database or play music. And sometimes this is referred to as being referentially transparent. And referentially transparent means that the function and its arguments can be replaced by its return value. So for an example, we are here defining a note. It has a name, C, and an octave, 4. Here we have a pure function, increment octave. It accepts a note and returns a new note with the octave incremented by 1. High C here is the result of that pure function. Play here is an impure function because it has a side effect. It plays music. And here you can note that you can pass in either high C or increment octave middle C and have the same effect. This is where the referential transparency comes in. So, you learn functional programming, and you remove all side effects, and now your program is useless. It's important to note that side effects are not bad. They include making an HTTP request, manipulating the DOM, printing to the console, or playing music. Side effects are not bad, but they are unpredictable and they are harder to test. So you should use your impure functions carefully and predictably. All right, now that we have a definition of functional programming, here are some of the tools that are important. Immutability. Immutability is the idea that variable state cannot be modified after its creation. You might be thinking something like, why? Why would you limit yourself by tying one hand behind your back? But there is a reason for this. One of the advantages is that it's less for your brain to track. Humans have a working memory. It's kind of like the biological equivalent to RAM. You can only keep track of so many things at a time. So by making sure not to change your variables, it's less for your brain to track. It also prevents unintentional side effects. Trust me, I know from experience that accidentally changing a variable in a function can be a really hard bug to track down. Immutability also preserves state. Think about it like a bank account. It doesn't just show your balance, it shows your starting balance and then all of your withdrawals and deposits. All right, higher order functions are functions that either accept a function as an argument or return a new function. So you might be thinking something like this. Here's an example. So we've got Tone.js is a framework on top of the Web Audio API. The Web Audio API itself is very low level and may be a little more than what you need. So the Web Audio API helps abstract it, become a little easier. Play note here is a higher order function. It accepts a note and it returns a new function. Play middle C here is the result of play note, and it is the new function. Add event listener here accepts a function as an argument. So add event listener and play note are both higher order. Play note because it returns a function, and add event listener because it accepts a function. So here's our first beautiful musical example. Here's our middle C. I promise they get a little better from here on out. All right, dealing with arrays. Manipulating arrays are an important part of all paradigms, and JavaScript comes with some array methods that work really well with functional programming. And there are two concepts that we covered that are important to dealing with arrays, and that's higher order functions. Each of these methods accept a function, and immutability, because each of the mentioned methods here will return a new array. So array.filter. Array.filter accepts a function that's run against every element. It receives an element, index, and array, and it returns a subset of the original array. So here, we're defining the melody. Is high here compares the note's frequency in hertz to middle C. And if the provided note is C4 or above, it will return true, otherwise it will return false. So we pass the isHigh function into the melody.filter, and we get only the values that remain. So here we have an unfiltered melody. And when we remove all the notes that don't pass the is high, we have the new melody. Array.map is similar. It accepts a function that's run against every element, and it receives the element, index, and array. But rather than checking if a value is truthy or falsy, it returns an array of the same length as the original, but with new values. So here, we have a melody, and we have our increment octave function from before. It takes a note and it returns a new note. And we can map the notes with this increment octave function. And then we have the same melody, but each note's octave has been incremented. Now we have array.reduce. Array.reduce is a little bit more complicated. It accepts a function that's run against every element, but in addition to the element, index, and array, it also receives an accumulator and returns an accumulated value. This is also known as fold or accumulate in some languages, and it is a more generic tool than filter or map. I sometimes hear that array.reduce takes an array and it returns a single value. This is true, but I don't find it to be a particularly useful distinction because all functions in JavaScript will return a single value. So I like to think of array.reduce as a value that takes an array and it can return any type. Filter, for example, will take an array and it will return a new array that is of smaller size. Array.map will take an array and it will return a new array of the same length but with different values. Array.reduce can return anything, whether it be a number or a string or an array. Filter and map, for example, can be written in reduce. So here's an example. We have a little bit longer melody. We define the notes and the length. Here we have a toLength function that's going to be passed to reduce. Total here is the accumulator, and note here is the array element. The method here accepts the function toLength and an initial value, and it will return the end accumulation. So we start with the initial value of 0, and then we add it to each note's length. So 0 plus 0.125 plus 0.125 is 0.25, 0.375, and so on until we get to the overall melody's length. So here, didn't update, the timer's supposed to go up. On my screen it says 1.625. Partial application. Partial application is an incredibly useful tool for writing reusable and generic functions, and partial application works by presetting or fixing some of the arguments to a function. So here, we've got the transpose function. It takes a direction, an interval, and a note, and it returns a new note. So here, up major third is a partially applied transpose. It accepts a note, and it calls transpose with up and a major third preset. So here we can convert C4 to E4, or B flat 2 to D3. And partial application is currently in stage 1 of the TC39 proposal. And if that goes through, then you'll be able to use the question mark to partially apply a function. So here, down minor 7th is a partially applied transpose as well. So you don't have to manually apply hard code each of the functions. So here, we can map, using array.map, these partially applied functions to an array of notes. Wish I could take credit for that melody. And here's it mapped down a minor 7th. All right, composition. Composition, I find to really be the bread and butter of functional programming. And composition is a technique to combine multiple functions into a new function. So here we're going to take a note name and we'll return a slightly detuned frequency. First, we have a function converting a note name to a frequency. For example, an input of A4, which is a note name of A in an octave of 4, will return 440. That's the hertz of that note. And here we're defining a function to multiply by a small percentage. So once we have that frequency, we can detune it. So an input of 440 would return 444.4. So compose takes two new functions and calls them from right to left. The right to left is because compose is a mathematical concept, and compose reads them from right to left. If you are, you can use pipe, which is a similar idea, but from left to right, and we'll be looking at that a little bit later. So here, get detuned frequency is a new composition that takes an input and it passes it first to frequency and then to detune up. So an input of A4 will return 444.4, so passing through the 440 value. And the pipeline operator is also in the stage 1 of TC39, and it would also allow for easy function composition. It would allow you to pipe a value through multiple functions. So here we got our A4 and our detuned A4. All right, putting it all together. I promised we'd be composing music with composed functions. Well, here we're going to be writing a function that converts a human-readable shorthand into a computer-readable array. All right, so can everybody read this? All right, so don't worry. I will zoom in on the important parts. So first, we're going to be importing some dependencies from Ramda and Tone.js. Ramda is a utility library similar to Lodash or underscores, but with a more functional approach. And you might note that there are a lot of functions I'm importing. One of the cool things about functional programming is that you take lots of small functions and combine them together with composition. So for example, parse name here is a function. It takes a shorthand note and it returns the name. So C4 at 8n would be a string where the C is the note name, the 4 is the octave, and the 8n is the duration. So it pipes through first to this regex, and that will return an array of matching strings. So any valid note name. And then it takes a head to return just the full string. So when passing in C4 at 8n, the match function will return an array of C, and then head function will take that and return just C. So C4 at 8n becomes array of the string C to just the string C. Parse octave is similar. It matches it to digits, and then we convert it to a number. And parse duration, similarly, will split at the at symbol, and it will take the last. So C4 at 8n will bring an array of C4, comma 8n, and then just 8n. Parse time here is a little bit more complicated. It takes a note and its context, and it returns a scheduled time. So here we have the array of notes. We're slicing it to only those preceding it. And then we map each of those to their length, and then we reduce those to a single value. And overall, this lets the Web Audio API know when to play each note. You're taking the duration of all the notes before an individual note, and you're taking the duration of them all and adding them together, and that lets you know when to play the new note. So here, Parse Shorthand is a composition of compositions. where it accepts a string and it will return an array of note objects. So first it splits at all white space, converting a string into an array of strings. And then array map here works like the array.map, but as a function, so that allows us to pipe into it. And apply spec here takes an object shape with functions. Each string in the array that we just split will be passed into each of these functions, and it will be mapped to an object of the same shape. So the string will be passed a parse name, and that'll be the value for the key name. The string will be passed a parse octave, that'll be the value for the key octave, and so on. So overall, with our parse shorthand function, which takes an array of strings, this input string will be split at white space, become this array of strings, which will become this array of note objects. And so that allows us to convert this into this. Or, or we can convert this into this. So, again, I wish I could take credit for those melodies. But so why do you want to use functional programming? I've heard that it allows for easier reasonability, easier debugging, easier testing. For me, I find that functional programming is really nice because it forces you to break down problems into their smallest parts. And by taking those small parts, you can combine the tiny solutions into larger solutions. So if you found this interesting and would like to go further, there are a few great resources that I would highly suggest. Professor Frisbee's Mostly Adequate Guide to Functional Programming. It's a great book available online for free. It goes very in-depth into functional programming. Also, I would suggest just looking into functional utility libraries, looking into their functions. Lambda is the one that I used here. Lodash-FP is a similar, uses similar functional techniques, but is based on Lodash. So if you're familiar with Lodash, that might be a better fit. And just looking at these and asking yourself, when might you use this function, I found really is a great way to level up. And also LambdaCast is a great podcast for all things functional programming. Thank you so much. If you have any questions, catch me afterwards or message me at adamgiese.dev. And the slides are available at composed.adamgiese.com. Thank you.